Welcome to lecture number 6 of module 3, that is a module states that is frequency and voltage control. In the previous lecture we saw that once we are going for the multi-area load frequency control, the number of state variables becoming very high, means the major objective for this control area that we must minimize the steady state errors, and then we had the integral controllers. For the two area we saw that we decided the Ki1 and Ki2, and based on that we try to reduce the error. But that sometimes the selection of Ki's is not optimal and the system may end up with the unstable control. So if you want to reduce the error, sometimes your system may be unstable. That is a major hurdle. So what we have to do, we have to design the optimal load frequency control of the AGC. Again, I will be discussing only two area case. So similarly we can go for the multi-area case as well. So the major problems are that the transient response in the designing of optimal control. First one is that the transient response of the system, that we require the system should be stable, the fluctuations should be minimum, means the overshoot must be less, and also the instability due to the higher order system. We will see for the two area system we are having 9 states. If you are going for more, suppose you are going for the 3 area system, the order will be again very high. And if you are going for higher area, then selection of controller is difficult due to the large number of control variables, and sometimes the controller you are designing may not be optimal. So our concern here that we can design some optimal load frequency control, and we'll see for the two area systems. Stability may be here what we are doing. This stability may be achieved by optimizing. Here it's not optimized, basically it is achieved by optimizing Ki and the bias up to some extent. But again here the controller may not be optimal, means we may have some optimal solution. So the stability, no doubt we can improve by choosing proper Ki and the bias value, that is B and the K. Here B is nothing but the betas, if you know. We can improve the stability, but we cannot say this whatever the value you are just choosing, it is a optimal one. So the need to design the optimal control, and objective is to minimize the transient fluctuations, and it should have the minimum control effort. So these are the basic criteria. Based on that we have to decide the optimal load frequency control, that is also called AGC. Now let us see the two area control system. We defined here, if you in the Laplace domain, this is your area 1, here this whole, this is your area 1, and here this is your area 2, and it is connected by your tie line. This is your area 2 and this is your tie line, you can say the model. Now what to achieve the optimal control? In the previous case we saw that these input, the change in PC1 and the PC2 were directly given here as an input. So the area control error where the change in this power, that is here P12, if you remember. So here it is a not PC, it is a P12 plus B1, that is a bias factor multiplied by the frequency of area 1. Similarly we had this ACE. Why I am writing negative? It depends upon the value of Ki. If you are writing here minus Ki, then it will be the positive value, so it is hardly matter. So AC2 will be nothing but your change in P21 S plus here beta 2 change in your F2S. So these were the control area signals, and they were directly given here, and then our loops were operating. So this is your, up to this here it is your primary ALFC, that is called primary ALFC loop. This is your called secondary, means here this loop is your secondary ALFC loop. Now what we have to do, first one is that we have to step for the optimal control that I'll state here. The conventional feedback loops should be opened. Means what we did here, this loop we have opened now. It is not directly connected. So we have just opened the loop and then express the system model into the state space form. Means we have to represent that x dot is equal to AX matrix plus BU plus FPU. So here A is, we know that it is your state transition matrix. So here we can express the system into the state space form. That's x dot must be equal to AX plus BU plus FP. Here A is your state transition matrix, B is your input matrix, and F is your disturbance matrix. The states, that is the X here, is known as the state vector, and it is consisting of all the states from x1 to xn, and in this case we will see we are having 9 states. For example, why 9 states? You can see the, now we are starting from here. So this is your state 1, that is x1, here state x2. Now why x2? Because you can say there is a st1. So there is some differentiation of that state, because we are writing here x dot, here there is s Laplace is there, so here we are going to another state. Now this x2, here again we are having stp, means here x3 state. Similarly here we can write x4, x5, here x6, and then we have another state here corresponding to this input to this. Here we are having x7, here we are having x8, and here we are having x9, because again we have 1 upon s here from this. So in total for the 2 area system we are having 9 states, means n is equal to 9. So here I have written the states are now 9 in number, and they are from x1 to here x9, and already I have shown you the input vectors. What are the inputs? Where just we are changing the generation. The inputs are, can be your m in number, but in this case m is equal to 2, means only we are having u1 and your u2. What are those? You can see here again. Input are nothing but these are your inputs. Means the inputs that we are talking, this input in this case here, what are the inputs that are coming here? That is your PC2, that is here I can say it is your U2, and here the PC1 is your U1. Those are coming here as input. So the U1 and U2 are the inputs here. They are coming here. They are basically, it's written something away. So it's U1 to this is one U1. This is your U2. These are the 2 inputs that we are considering. So your U vector here means that is M is 2 in this case. Now another one is your disturbance vector, that is a P. It is your, again it can be K in number, but in this case again we are having 2 disturbances. Means what are those? I can write here P1 to P2, and these are nothing but the change in the loading, and that is nothing but here it is your PL1 and your change in PL2 are the disturbance vector. So whole this system here states we can represent in terms of state space representation, including the input vectors U1 and U2. We are having the disturbance vector here, that is your P1, and here we are having is equal to P2, and we can write completely the state space form. Here the main objective is why we are trying to that. Normally for the optimal control, the input is created by the linear, here U1 and U2 are created by the linear combination of all the states, means that is a full feedback. Here what we are getting, we are taking only one state here. Here we are taking only one state. But in the optimal control design, we have to take the linear combination of all the input state, means from starting from x1, x2, x3, x4, x5, x6, x7, x8 and x9. So U1 will be the combination of all with the different scaling factor, means different k, that is a k gains. So we have to now write the state space form, and then we'll see how we are going to change. So if you are taking input is the, that is from all the state, then it is called full feedback. It is not, if you are connecting this one as x8 to U1, then it is not a full feedback. So we have to write now the state space representation of this model, and for that we have to consider, let us take first one here for writing for this state x1. How we can write here? We know that this is a transfer function of your governor, this is a transfer function of a turbine, this is the power system transfer function. So what we are going to do, we are going to write what means your x1 will be nothing but the input which is coming to this transfer function, that is nothing but here what is that x3 is the state which is coming here, means we are getting minus x3 by r1. Why minus? Because here the minus sign is there, plus your input is u1 here, that is multiplied by this transfer function, and that transfer function is nothing but your 1 over 1 plus stg1. From here we can easily write this expression. Here we can write 1 plus stg1 x is equal to change in here pc1, that is nothing but your u1 we have taken, and minus x3 upon r1. From here what we can do, here now we can again simplify this by what we can do, we can write this stg1 x1 is equal to, I can write minus x1 minus x3 upon r1 plus u1. So what is this? This x1 is x dot, so I can write here x1 dot, and this tg1 will be divided, so I can write here x1 upon tg1 minus x3 upon r1 tg1 minus u1 upon tg1. So this is the first state x1 state space representation, and that is written here, you can see this, that is related with the equation 1. Similarly we can write for equation 2 also. Equation 2 you can see again how we have related this x2 with related to your x1, means I can write here this x1, or you can say x2 will be equal to your x1 state multiplied by this transfer function here, and that is nothing but your 1 over 1 plus st1, or this will be multiplied here, and then we can write here that this state expression 2, means we denoted that your x2 here 1 plus st1 is equal to your x1, means we can write, sorry this is not dot because s will be coming here, so I can write x2 will be equal to minus x2 upon tt1 plus x1 upon tt1, and here this can be replaced and we can write x dot, and you can see thus we have written this equation 2. Similarly we can write for x3 dot, and x3 dot is nothing but what we are getting from here. Now this is no doubt it is very important, here we can see how many inputs are coming to this transfer function, that is your power system transfer function here, including the load release, etc. For this we can write here this x3 will be all the inputs here, algebraic sum multiplied by this transfer function. So I can write here, I can write a very easy way, that your x3 will be nothing but this transfer function, I can write this kp1 here 1 plus tp1 yes, and then multiplication of all here, that is input state is your x2, that is a positive, minus x7, that is going here, it is x7, and minus p1. So here we have to write in this fashion. So we are getting x3 state in terms of x2, x7 and the disturbance vector of p1. Why we are writing 1? Because we have considered this is your area 1, this is your area 2. So the 2 denotes area 2 and 1, that is a subscript denote that one. So what we can do, we can again multiply here, and then we can write simply this x3 dot, or in other words, simply way I can say we can get this expression for x3, that x3 dot will be equal to minus 1 upon tp1 x3. You can say always this x2 is here, because if 1 plus st is there, so one term will be with negative of this, plus kp1 upon tp1 x2 minus x7 was there, so this coefficient will be arising, plus minus kp1 upon tp1 p1, and let us, it is equation 3. Similarly, we can write the equation x4, and this is similar to your equation 1. Why? You can see here from this figure, this x4 is just exactly similar to your x1 here. This x4 is similar to x4, only the difference is that here the parameters are tg2, r2, and your f2, or you can say state x is coming. So I can simply say that we can, from the equation 1, we can write equation 4, that is your x dot 4 will be equal to minus 1 upon tg2, here earlier tg1 was there, x1 was replaced by x4, here x3 in this case it is x6, tg2 into tg r2, plus here your now input vector is 2 divided by tg2, so we are getting equation number 4. Now similarly we can write the state space representation of x5, and that will be similar to your x2, and your x6 here will be similar to your x3. So this is for your area 2. Here this 1, 2, 3 are for area 1, and we'll see x7 is your tie line bias, tie line control. So we can write this x5 similar to your the previous one. I can say simple, you can see this is your x5. I can even though write from x2, this x5 dot will be minus 1 upon tt2. x2 is now equal to your x4, no, is x5, and plus your x1 is your nothing but your x3, in this case upon tt2. No, here x5, so it will be x4, because 3 is for area 1, so it will be x4 here. So you can see here simply this x5 dot is equal to minus 1 over tt2 x5 plus x4 upon tt2. So we are getting equation number 5. Similarly, we can write the x6 that is related with your x3 of area 1, and we can replace all this one subscript here by 2. So you can say minus 1 over tp2 x6 plus kp2 upon tp2 x5 minus kp2 upon tp2 a12 into x. Here another parameter is appearing due to the change in the base, minus kp2 upon tp2 into p2, that is another disturbance vector that is occurring in area 2. So we are getting equation number 6. Now we have to again write this is for the state 7. State 7 we can see again here what we are getting, you will use earlier one, means x7 was related here, it was the 2 pi t12 divided by s, and the inputs that are coming here your x3 minus x4. For example, you can see here very easily with this block diagram, here x7 is equal to multiplication of the input that is coming here, so it is a positive, here is a negative, so x3 minus x6 multiplied by this here, and we are getting x7. So we can write very easily this equation, and I can say simply here s will be coming here and this will be cancelled out. So I can write x7 dot, it is your 2 pi t12 x3 minus 2 pi t12 x6, and you can see this equation we have written here can see the 2 pi t1 to x3 minus 2 pi t1 to x6, that is for your tie line model. Now we are having another one, that we are going to have some integral controllers, and that controllers are denoted by, for area 1 it is x8 and another state x9 for your area 2, and then we can write, and we know that this x8 here is related with nothing but your ki upon s here with the minus sign, plus we are getting the state for the one case. Here we are getting your x3 multiplied by b1 plus here that is your coming x7. For example, you can see what I am writing. Let us see this block diagram here. So this x8 will be equal to the inputs which is coming here as well as here. So what we are getting, we are adding here this and this together, then multiplied by this negative ki, we are getting the positive. So this x3 multiplied by b1 and this p12, that is x7, here both are added with the negative sign, then multiplied by ki, so we are getting that. So we can write this here for x8 is minus ki 1 x7 minus b1 ki x3, that is for integral controller of area 1. Similarly, we can write this x9 dot for integral controller of area 2, and having the bias factor b2 and the integral gain, that is ki2. A12 again it is appearing due to the difference in the bases of area 1 and area 2. If both are equal bases, having equal bases, then A12 will be minus 1. So all these 9s means we are having states from 1 to 9, that can be written as the matrix A having the states 1 to 9 plus matrix B here, and inputs are U1 and E2, and the disturbance vector here your P1 and P2. Now the order of this matrix will be your 9 cross 9, that is state transition matrix. The order of B will be your 9 cross 2, and this disturbance vector will be having 9 cross 2 because we are having 9 states, and the 2 disturbance here similarly for this. So we can now from all these 9 equations we can represent the matrix A as follows, and this will be your matrix A. So we are getting this state transition matrix A here, that is, you can see the beauty of this matrix is that we are getting this matrix, most of the elements are 0. So this matrix is not full. So you can see in one row we are getting 2 elements, 2 elements, here 3 elements, here 2 elements, 2 elements, 3 elements, 2 elements, and 2 elements, here again 2 elements. So in the most of the cases we are getting 2 elements, and the 2 rows only we are getting 3 elements, and the remaining here they are 0. So now we can count how many elements we are getting in this state transition matrix. So this is very sparse, highly sparse matrix. For example, you can say we are getting 2 here, 2 here, we are getting 3 here, we are getting 2 here elements, 2, 3, 2, 2 and 2. So you can say here we are getting only 20 elements in total out of here 81 elements. So we are getting 71 elements 0. Similarly, if you will see the B matrix, you can say only we are getting 2 elements here corresponding to Tg1 and Tg2, that is coming, and your F disturbance matrix also we are getting the 2 elements here, and others are 0. Now after we have represented the system by opening the loop, we are representing the system into the state space representation. Then in step 3, to design the optimal controller, we have to generate the control inputs U1 and U2 by means of a feedback of all the states. Means we have to take the states of all this x1 to x9, then I can say this U vector will be your k multiplication x dot. You know this x is 9, so it will be your 2 cross 9 matrix, and you can see means your U1 will be nothing but k11 multiplied by x1, here k12 multiplied by x2 till k19 multiplied by x9. So we are getting the linear combination of all the states, and then we are feeding to the input 1 here, and again you can say only the varying quantities here, the gains we are deciding, and we have to calculate the gains k11 to k19. And again here for the second input also we are getting k21, k22 and k29, means we are getting again the 9 here gains and 9 gains here. So we have to calculate the gains optimally. This means now we are having 18 gains. 18 then we have to calculate. So here let us see what is meaning of this input. It means that whenever we are giving here your, that is the input, that is your PC1, that is U1, it is nothing but your change in PC1 reference. So this is basically we are getting the summation of all the states, and that is coming with the here gain, I can say k1, k11, and that is coming here, let's suppose is your x1. Similarly we are getting x2, here your gain is your k12 and here adding, and similarly we are adding x9 with the gain k19, and then finally it is here added. So here we are adding all the states with the some constant, and then we are feeding to here. So this is the way that we are designing. One thing we saw in state space form, as we had vector like x dot is equal to your ax plus bu plus fp. But in standard form always we write x dot is equal to ax plus bu, means there is no disturbance vector. So we have to eliminate this vector, and then we have to go for the standard form, then only we can design the optimal controller. For that we know that for the constant disturbance vector pi, if the disturbance vector is constant, then your x dot here, that is the matrix here x dot, will be equal to 0. Means now we will get the steady state states, that is x, all x vector will be having steady state, and also your input will having the steady state values. So for constant disturbance vector, this means we have changed some loading. Let's suppose once fixed, what will happen? The time change in the states will be 0, because all the states will attain the steady state condition. So here x, this will be 0. Now it will be equal to your a x here ss, that we have written here, means a multiplied by your steady state states plus b your input states, that is coming from your all the inputs states, plus here f multiplied by here the p disturbance vector. Now we know that x steady state during the transient condition, means at any state we are getting this x is the two component, one is called x prime, that is a transient, and another we are getting xs. What happens when the transient is die out, means this component becomes 0, so we are getting the steady state value. So we can say any state here can be represented by the two terms, one is your transient and another your state value, that is the steady state. Similarly, we can write the input vector u, that will be equal to the transient input plus your steady state input, and we can delineate into two different transient and steady state values. Now we can put this value here in your condition, we can put here in this expression, in this state space form of our proposed state space representation. Now what we can do, this x will be represented by your different value. Just what I am going to do, I am going to put here this x dot is nothing but your x prime plus xss, and here I am going to put dot, means the time varying quantity. Similarly, I can write here a, now x prime plus xss, plus here I am writing b u prime plus uss, plus of course f plus p. What is happening? if you are taking the Laplace here time domain of steady state, it will be 0 as we know. And now we are going to represent, we are using from the previous case, means I can write here a x prime plus b u prime. Now plus I am writing another factor here, the remaining, that is a x ss plus b u ss plus your f p, another factor, and this is equal to your x dot prime. What happens? This is nothing but 0, you can see from this expression, because during the steady state always will get this relation because the transient is die out. So this is equal to 0. So we are getting x here, this is your 0, so that is vanished. So we can get this expression here simply, that is a x dot prime is equal to a into x dot plus bu. Here we are writing only for the transient case, means steady state is vanished out, and then we have to design the controller accordingly. So what we decided here in the previous case, again from here we can write your u prime plus u steady state, that will be equal to your minus, normally why I am writing minus, because here we are taking the integral controller with the negative input of areas, because once it is increasing we have to decrease the frequency rises, we have to decrease the output. If the frequency falls, we have to increase the input. So the negative sign is used, and then it is the x matrix, that is your x prime plus x axis. We know it very well. So we can use here this relation again in terms of your transient as well as in steady state conditions. And then we can, for the optimal control system, the state and control vectors should have the 0 steady state inputs. Means for the optimal control, the system state and the control vectors should have 0 steady state value. We don't want that this state should change here and there. So what we'll get? Here already we defined this. So for the optimal control, the system state and the control vectors should have the 0 steady state value. Then what we can do, means this is 0, this is 0, so I can write u prime is equal to minus k into here, again these are the vectors, and it is x prime. So the u transient will be equal to minus k times x transient. Now in step 4, now we have seen this, we require this matrix k. So the feedback k, matrix k is to be determined, and normally what we do, we use this pi, that is one performance index here, and that is here integration of a performance here, performance index, that is your x prime into your q x t here prime u r u t dt, where r and q are the symmetrical matrices, and determining through the design consideration, k is obtained from the reduced Riccati equation. So the normally what we do, certain performance index is minimized, and that performance index here is called pi. It is not a proportional integral, it is a performance index, and that here we integrate from 0 to certain here value, that is we go for the infinite basically, and then it is your x prime into q x transpose plus here, and these two q and r matrices are the symmetrical matrices, and they are determined through the design considerations. The value of k is obtained from the reduced matrix of Riccati equation, and the Riccati equation is here is nothing but your, this is a Riccati equation, that is your, I can say A transpose, now I can write S plus S into A minus S B R inverse B T S plus your Q is equal to 0. Means knowing the value of, normally we try to minimize this, and by that minimization we get the Q and R values. If you are putting the Q and R matrices here, B matrices is fixed, A is also known to you here, it depends upon again the state space we formed that. Now from this equation we require the matrix S. So means matrix S must be determined, and then we can relate this, what is the K in this case? K will be, the matrix will be nothing but your R inverse, now your B transpose, now it is your S. Means once you are getting S matrix, you can get your K matrix. So for all stable cases, all the eigenvalues of A minus Bk should have the negative real part. Now what is happening? You can see we designed here x prime that is equal to your Ax prime plus, if you remember, here we got Bu prime. Now we saw this U prime is nothing but minus K x prime. You remember here already I have written this value here. So if you replace this, we are getting A minus Bk matrix here, and then it is your x prime. So this here, this for all the stable here, we should have the eigenvalue of this should have the negative real part. If it is not having real negative part, then system will be unstable. So we want that stable system, so we have to take the eigenvalue here. Means the value of K should be such that we should have this negative eigen, means real part of eigenvalue should be the negative. Now in this way, what we should do, you can say it is very complex system. Now we saw that how we can get the optimal gains, optimal controller design. But the major problem is that for the here it will require the full information, state information, because we used, as I said, if you remember, I used this your U1, it is nothing but the summation of I can say K1I xi, here I is equal to 1 to all the state here in the 9. So what is happening? You have to have the information gains we determined, of course no problem, but this x state, that is x1 to x9, to determine it is very difficult sometimes, and also it is very expensive. Sometimes if you want to obtain the state of the governing system, you want the state of turbine system, already we have used, you know, this very simple model. The for the turbine we have used very simple, we have not used the reheating and other thing. If you are including those also other time constant, then this system becomes very complex, because for large you can assume that is a 2 area 9, and then for the multi area, let's suppose 4 5 areas are connected, that state here may be the 30 or 40, and it is very difficult. So what we have to do, we have to overcome. So for that, what normally we do to overcome this disadvantage, normally we generate all the state locally by use of observer or Kalman filter, and then by processing the local output. So we can generate these state, means we cannot measure if, then we have to generate these state, because we have decided this optimal gains, we have to use this, so we can generate these using the Kalman filter or local observer. But this gives higher order system and cause instability problem. Now what is happening, we are designing another Kalman filter, so it will again some states will be included, and then that may cause the instability of the system, that is again very dangerous. Or what we can do, we can use suboptimal scheme implying only the local states of that area. Means here instead of going for all these cases, what I can say, now your U1 can be simply I can say K1 1, another constant. Now I can say here your x1 plus K1 2 x2, and plus here another state, here it was K1 3 x, you can say x3. So only the 3 states just I am considering, or at most we can consider another state, I can say x1 4, here that x7 which I was using. So for one area we can use the local signal, that is very easy. For example, we have the 2 area, let's suppose we are just designing the controller, and another state, let's suppose for Rajasthan, and taking the input signal for the generators from very remote place, and here taking, there will be lot of errors, lot of noises. So it is very difficult, as I said, and expensive too to get that signal. So it is possible that we can go for the suboptimal system, that is also good, because we are having some optimal controller here. Then we have to take the design the system in a such way, and we have to choose these gains, and we have to take the states locally. So if it is difficult to get the optimal controller, then we can go for suboptimal control, and that is good enough for that. So what we saw in a area, there are so many generators, and then we have to decide, we have to allocate the load change in that particular area. Suppose there is a 100 megawatt load increase in one area, then this 100 megawatt must be shared by all the generators, and then we have to decide how they will be sharing, and that basically is based on the some participation factor, PF normally we call it. Is not a power factor, it is a participation factor. So each area consists of many generating units, so this is valid. Output of each unit must be according to economics, means we have to set their units so that the cheap units must generate the full loading, then expensive generators should come later on, because always here we have to generate with the minimum cost of generation of electricity. And we also know that the system load is always changing. So if it is always changing, the loading should also keep on tracking that, and the loading should also change. So here the economic load dispatch must be done to meet that load demand in the economic way. So the individual generator output can be decided at the base point, what is presently loaded, plus some participation factor multiplication by the change in the total load. So let's suppose this 100 megawatt load is changed. So if the participation factor of that one is 0.1, then 1 multiplied by 100 means it is, here it is a point, let's suppose the PF of 1 is 0.1, and here change in the load, here let's suppose 100 megawatt, then we have to multiply this, means the 10 megawatt will be changed from the base loading. Base loading means where the generator is loading right now, and now there is some change, means whether increase or decrease, then we have to increase and decrease according to the participation factor, and that participation factor is defined for any ith unit. I will be equal to change in the generation in ith unit, how much you are going to change, divided by the total change in that area, total change in the load. So that's I have written here, change in generation at ith unit in area divided by total change in the generation required in that area. Always this participation factor must be unity. Why? We can see this. Let's suppose this is a P of I is defined as here change in your PGI divided by your change in here P total. Now if you are summing this, what is happening? You are summing this. Summing this is nothing but the generation of all the units, that is nothing but is a P total. So we are getting change in P total divided by change in P total, and this is your unity. So the total of the participation factor, suppose your units are having 2, so the participation factor 1 is let's suppose 0.1, and other P of 2 is let's suppose 6, so your P of 3 will be automatically here 1, here 4, means 0.4, means we have to 1 minus here the participation factor this plus this, means 0.1 minus 0.6 here, so we are getting, sorry, it is a 0.3. So the participation factor is always related with the summation of the participation factor of all the units, that it will be equal to unity. So I can say this ith now desired with the change in the loading can be written as the PI base, means which is loaded right now, plus the participation factor of that ith here multiplied by the change of the total load in that area. If we will sum together, means sum of ith units means all the units, if you are adding the desired change, here again you are going for the desired base plus here the P total. Now this P total is nothing but, what is that? Here change in P total is the total power, the new total, how much load just we in system and what is right now we are loading. So this here the P new total means load that is increased from the base case minus which was on IS, means that is change in the total load, and then we can relate with this equation. Now we can again relate this one in this overview of AGC logic. So let us see the overview of AGC logic, and that is based on your base point and participation factor method. what we do, this is for the single area, this figure shows for the single area. We have here the single area and we are measuring, this is area 1 I can say, and we are having some measurements using the telemeter data. We are measuring the system frequency here from this area, and also we are measuring the tie line power from all the here tie lines. So here the meter, as I have written, the telemeter tie power flow megawatt, that is a sum together, and now we are the total sum of the tie line power that is flowing from the area 1 is summed together, and then we are just subtracting, that is the reference value, that's how much is set that will go from that area. So here that is subtracted. So whatever we are getting here, change in from, you can say, area to other areas. This is a P12 if you remember. Now the frequency we are measuring, and we are having some standard or rated frequency, that is you can say F naught, and this is your F. We are measuring from the system. If there is any difference here, what we are getting change in the frequency, and that is multiplied by the bias factor P, and here both are here added together, and then finally it is your area control error that we have defined in the previous case. So this is ACE logic, I can say, means area control error logic. Here we are not going for the optimal control, it is a normal control, and we'll see how we are incorporating other base point loading here. So this is your ACE logic, means we are measuring the system frequency and the tie line power flows, and then we are getting the ACE, and that is come to here. As you know, it is a very standard, and already we have defined this ACE is nothing but your change in F, that is multiplied by B plus your change in P12. Here again we are writing with a minus because we are using the integrator, because change in the frequency we require more power. So here I have now what we are doing, this is coming here. We want to calculate, this is your error. Now we can also check at the same time, we are measuring the real powers of all the generators, that how much error in this your present unit and the desired one. Means we want that this must be desired, there is some error in the previous state, means previous condition, previous time, that what is the error from your actual, that is the measurement from the unit here, and the desired one. So that difference here for all the units, here we are having n units, you can say, so they are adding together here, and that is now here again added together here, that error, and then this ACE is going to be here. Why we are adding here? This will be your negative sign because we are taking here the positive. So that will be added again because we want more generation. So here the K we have taken positive, then it is your negative. If you are taking K negative, then it will be negative, and this will be your positive, and then we have to take care. So now we are integrating, you are using, that is a integrator, that is a reset controller, and finally here that is your change in the P total we require here. Now this P total, what we are going to do, we are also measuring what is the current loading of the system. Then current loading of the system, that is a summation of all the PGIs, here they are coming, and finally it is added together. Then here we are getting that value, that is called your the P desired. Here we are getting some value here, and then this value we are getting the P desired, and this P desired value is now subtracted from the P base. As I said, the P base is summed together. Here the P base we are taking, how much we have to set the P base. Basically this P base is nothing but it comes through economic load dispatch. We know that here is the demand, how much we have to load so that we can achieve the economic loading. So this P base is basically decided again based on these generators, this PGI, and we can get this P base for individual. So this is now subtracted from here. Now the P total that we require is nothing but P desired minus summation of P base, as I in previous equations we defined. So now the change in the total power in that area is distributed over the various generators from 1 to n here. And again we are using the participation factor, means for one generator is a PF1 value, PF2 value, PF3, and so on and so forth, and then it will be shared, and then finally we are getting here the value someone here, and that value is going to be added with the P base, that will give you the P desired of that one. Means this change plus the P base will be giving the desired of 1, and then this desired 1 is compared with the actual one, and then we are giving raise and lower, that is the input signal to the corresponding generator, so that whether we have to increase or decrease accordingly. Similarly for here, for this unit also, this coming after the PF2, we are adding with the P base 1 to here, that we are getting the P desired unit, and then we are comparing with the actual here measurement. This is actual, and then we are giving raise or lower command to change that one, and this area basically it is called generation allocation logic, means how we are allocating the generation. So it is written your generation allocation logic. If we are going at particular unit and we are changing the unit based on the required logic, that is called your unit control logic, and you can say for each unit we are having one logic. So you can say that is in dotted line, you can say unit 1, unit 2, unit 3, and so on and so forth. So we are having three logics: ACE logic, this generation allocation logic, and the unit control logic. Another logic here we have not shown here, that is the P base, which we calculate. It is nothing but we just solve the economic load dispatch, and let us see how it is coming. So here the P base, the output I will show here in the next, just I will draw a block. Means what we do here, this is your economic load dispatch. What we do, we measure the current, this PG1 here, to your all the inputs are measured, telemeters, means all the generations we are getting the inputs that we are measuring. Now here we are doing the economic load dispatch. We know the total sum, total demand of the generation, and based on that we can, now the output of this ELD will be your, that is called P base. This economic load dispatch is normally done 3 to 5 minutes in every interval, and then the P base is set. So this is called your economic load dispatch logic. Here our intention is to minimize the total cost of the system, the total cost of generation basically we are talking here in economic dispatch. So it is a summation of the cost of here of the generation of I. Here I can say that is a function of real power output, and then we have to minimize subjected to the various constraints, that is the power balance equations. So this is your economic load dispatch logic. So what we did, we had another unit that is called the telemetry. If here telemetry, in telemetry we are measuring the system frequency, that is only one input. We are measuring here the power, that is the PGIs of all the generation of that unit, and we are measuring here the tie line that is going from that area. Means this is your area, we may have a different tie lines here. So how much net schedule, that means we can measure this, 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 and this, and then we can decide that I can say I1 from area I to 1, and then we are processing here and we are doing whole this logic. So this is, if you are combining this ELD, then it is called your AGC included with your economic load dispatch, here combined logic. Here we had this AGC, that is automatic generation control, plus economic load dispatch logic we are including, then it is called combined logic of AGC and ELD. So we know that whenever you are changing, why the ELD included here, because economic load dispatch means you are changing the real power, and once you are changing the real power, then the load is changed, frequency is changed, so it is related with the complete frequency control, and we discussed. Here, other than this economic load dispatch, there is another is called optimal reactive power dispatch, and that optimal reactive power dispatch is changing the voltage, or you can say the reactive power generation, thereby we are changing voltage, and the system losses and the injections are different one. And then we'll say this another loop, that is your voltage control loop of the alternator, we'll discuss in our next lecture of the same module. So now I can recap what I discussed in this first 6 lectures that was related to your frequency control. In frequency control, in this we model the various components, those are related for the frequency calculation of the system, means we model governor, turbine, power system, and then we saw that we require some controller because the frequency error due to the certain disturbances change in the loadings in that area, it is not 0. Then we propose our PI integral controller, that is a reset controller for one area. Then later on we moved that if the areas are interconnected, as we saw there are various advantages and disadvantages for having the interconnections. So then we model the tie line power model, and then we analyze for the two area case having the tie line concept. Then we also moved ahead to design suboptimal controllers so that we can have the stable as well as optimal control logic, and then we define that one as well. Finally, we just realize with the diagram here, with this diagram, that how we can achieve this complete overview of AGC logic, including your economic load dispatch. And we saw that for any particular area, the major objective is your nothing but here that AGC objective is that the total system frequency are very close to its normal value, means we have to operate to its rated value, and to maintain the correct value of interchange power, always we have to be maintain that, means there will be, as I said, this change in the frequency error should be 0, change in your tie line power flow from any particular area must be 0, and then means whenever there is a change, we have to meet that load from that area only. So these are the basic AGC logic. In economic load dispatch logic, that we have to reset because we are going to change, once load is changed, we are going to share the load. Why not? We have to achieve the economic loading of these criteria, these generators, and then we can get the minimum cost of generation. So the combined logic of this AGC plus ELD also I discussed, and then so far we discussed only for the frequency control, and then in next lecture we will see the voltage control. We will also model the exciter, we will also see the various loops, and we will check about the stability, whether it is stable or not, because the gains of exciters are also very important, and we will see in the next lecture. Thank you.